So far in our circles unit, we've learned a lot about angles and their relationships inside of circles. So let's do a quick review about what you should know already. When you have a circle, if you draw an angle to the center of that circle, let's say this angle happens to be 40 degrees. We know that this is called a central angle, and a central angle should equal its intercepted arc. So this arc over here that is being cut off by the two endpoints of that circle, or I'm sorry, of that angle, should also be a 40-degree arc. That's a very important theorem that we need to know. We should also know that if I have a different circle and I draw to a point on that circle instead of the center of the circle, that this is called an inscribed angle. And an inscribed angle does not equal the intercepted arc. So let's say this was a 40-degree angle as well. That means that the intercepted arc, again from this point to this point, is going to be twice as big because an inscribed angle equals half of the arc. So this arc would have to be 80 degrees and the inscribed angle is half. Those are the two angle relationships that we have so far. So let's see what other types of angles we get inside of a circle. You might also get what is called a tangent chord angle. These are very cleverly named because what you have here is a tangent, AC, hitting a chord, CD. So chord, tangent, that's a chord tangent angle. And what we know about this is the measure of a tangent chord angle is also half of the intercepted arc. What people get difficulty here is the 2 points that create the intercepted arc would be point D, and if I follow this angle to C and then A. So this is angle ACD. The intercepted arc actually starts between those 2 points. So the vertex is one of the points. So the intercepted arc is going to be between points C and D. If I look at angle BCD, that's going to have a different intercepted arc. Arc BCD, so BCD, this angle right here. The points that are being cut off of the circle would be point D and point C again. So it is also a tangent chord angle, and its intercepted arc is everything between those 2 points. So what we're going to get is that that angle is half of the intercepted arc. So let's say that the measure of arc CD is equal to 80 degrees. So if that arc is 80 degrees, then the measure of my angle BCD is exactly half of that, and it's going to be 40 degrees. So let's see if we can use this theorem. Very simple. The measure of the tangent chord angle is half of its intercepted arc. So ACD, that would be this angle. The intercepted arc is going to be between C and D, which is 220. So angle ACD is going to be 220 cut in half, which is 110. On the other part of the circle, we have angle BCD over here. So that intercepted arc is 140. So since it's a tangent chord angle, it's going to be half of the 140, which is 70. What's nice to know is it's exactly like the inscribed angle. The way I think of it is if you have a vertex that is on the circle, if the vertex is on the circle, the intercepted arc divided by 2 will be the measure of that angle. Now you will not get an angle on the circle if you have what's called a chord-chord angle. A chord-chord angle is exactly what it sounds like. It's created when you have 2 chords intersecting each other. So over here you can see chord FJ is intersecting chord KH, creating this chord-chord angle. So you have 4 of them. FGK would be a chord-chord angle, and we know it's going to be congruent to HGJ because those are vertical. And then you're also going to get chord-chord angle FGH and KGJ. So those are what we call chord-chord angles. How this works is the measure of a chord-chord angle is exactly half the sum of the intercepted arc and the arc of its vertical angle. So you got to be very careful with this. So if we're finding the measure of FGH, FGH would be this angle right here. Now the intercepted arc of that Again, if we follow this out, we hit point F. We follow the angle out, we hit point H. So the intercepted arc here would be FH, which is 80. But it says the measure of a chord angle is half the sum of the intercepted arc and the arc of its vertical angle. So we have to look at the vertical angle right behind it, and we're going to follow that out, which has an intercepted arc of 150. Again, if you draw out, we're going to hit point K. Drawing out along the vertical angle, we hit point J. So the intercepted arc would be arc KJ. So FGH, the measure of that angle is going to be 80 plus 150, and then half of that. So everything's half, but we have to add here because it's inside the circle. So we get 80 plus 150 is 230. Half of that sum of 230 is going to be 115 degrees. We're going to get the same thing when we try and find the measure of angle FGK. So FGK would be this angle. So I'm going to trace that out, FGK. The intercepted arc is 60. The vertical angle to that is right here, which would be HGJ, and the intercepted arc of that is 70. So I need to take half the sum of those two intercepted arcs to find the measure of angle FGK. So it's going to be 60 plus that 70 divided by 2, which is going to be 130 divided by 2, which ends up giving me a 65-degree angle for angle FGK. So what we have to do is figure out what type of relationships am I looking at, because you're going to get lots of angles from chords and tangents and secants all over your picture, and you've got to recognize what you're looking at. So here's a good example. Line ST is tangent, that's important to understand, and it says the measure of arc RQ is 80, so from R to Q is 80 degrees, and it says QT is equal to RT. That should be enough information to help me figure these things out. So what the first thing I notice is this intercepted arc of QR is being cut off by angle QTR. So this angle right here is an inscribed angle because it's on the circle right here at point T. And an inscribed angle is equal to half the intercepted arc. So this inscribed angle is 40. So angle QTR, 40 degrees. When it asks me for angle QTS, again, let me get rid of that. We know this is 40. These are the same. Angle QTS goes from Q to T to S. Now you can think of this as a chord tangent angle, but what I like to think of it as is this vertex is on the circle. So I have to identify its intercepted arc. Well, the arc being cut off or inside that angle is arc QT. So I need to know that angle, and angle QTS will be exactly half. Well, all I have is that this arc is 80 degrees, and I don't see a diameter. There's no way for me to figure out that this is 100 or 120. So I have to think of another theorem that says if two chords are congruent, then so are their arcs. So these two arcs, RP and QT, are equal to each other. So if I only get 360 degrees total, minus the 80 that I already knew from arc RQ, that's going to leave me 280 degrees left in the circle. Split evenly or divided by the two congruent arcs is going to leave me 140 degrees for each arc. So I've got 140 here and 140 here. And now I do know that the intercepted arc of angle QTS is 140, so this is going to be half of that, which is 70. And then likewise, if I'm looking for RTP, that would start at R to T to P, so that's this angle. That vertex is on the circle, so it's going to be half of its intercepted arc, which is everything between R and T. We figured out that that's 140, so RTP is also a 70-degree angle.